The test procedure has been to measure the electrical output with different connections, loads and throttles. Bike speeds and gradient performances have been estimated and a power control method indicated. Next are the connection options. The open delta on the left rectifies the output of each phase winding. It should eliminate harmonic losses, but it is otherwise relatively inefficient. The conventional delta in the center is more efficient, but can lose power in circulating third harmonics. The star on the right should be best for higher voltages. As shown previously, its output has a high ripple content. Each option uses 12 diodes connected appropriately. Now another look at the test setup. The test bench gives manual control of the throttle and field current with 8 selectable power loads. 4 meters read output, throttle, field current and engine speed. The procedure in each test was slowly to approach full throttle while increasing the field until the maximum output was reached. The results were processed for graphical display. Here goes. And now the first results. Open delta gives a maximum of 650 watts at a typical alternator efficiency of 65% of the input power. The principal loss is deduced to be hysteresis right across the range and very sensitive to field current. There is an additional ohmic loss at the high current bottom end. Reduction of these two villains should be feasible by building a machine with less and better iron and possibly rare earth field magnets. Efficient wide-range power control may then become an issue. The required field current is always under the 2 amp limit of the controller, rising both with output voltage and to overcome the voltage loss at the bottom end. With the chosen motor, 36 volts is nominally 15 miles per hour in an unloaded 26-inch wheel. Next slide please. The closed delta generally gives improved output due to its paralleled phase resistance. The open version, however, keeps some advantage at the bottom end, presumably through harmonic recovery more than offsetting the resistance loss. The field current is similar to the open delta, but is lower at the bottom end. At the load corresponding to the stopped hub motor, the starting push in the back to the rider should be about 20 kilograms. Next is the star. Star has a similar maximum to the others, but extending over a high and wider range. Bottom end power is reduced, however, and the starting push in the back would drop by 5 kilograms. Field current reaches the 2 amp limit at each extreme due to the higher output voltage and resistance effects. The star option was used in the original bike. Change to closed delta in the licensed version confirmed the improved starting from standstill with somewhat reduced top speed. We may conclude that a switched overdrive is the way to go. Next, performance predictions. Here the dashed lines show approximate powers to propel a 100 kg bike, including rider, up gradients from flat to 1 in 8, assuming the nominal voltage to speed equivalence. A factor in the equation of 1.25 concedes hub motor inefficiency. Delta should maintain some speed at 1 in 8, and 15 miles per hour at 1 in 20 would leave about 200 watts for acceleration. Star significantly extends the speed on the flat, but the bike would fail to move at more than 1 in 8. These environments all involve a little more power than the declared average rating of the hub motor. Working at the most efficient bike speed with occasional pedal assistance may give some protection. It hasn't grumbled yet. While we are reviewing the results, a simple control scheme may be envisaged. The tests have included full, half and quarter throttle, as measured by a potentiometer on the carburetor. The resulting engine speeds were all observed to be almost constant over their effective ranges. Next, the same data are plotted here against throttle opening, showing that a minor addition makes the potentiometer reasonably track the best speeds. Speed control by field current may then be exercised through a suitable error amplifier.